writing the warm-up down at this point. If you're not watching the computer, just hold on. We'll get there shortly. Come look at this one and tell me who's this handwriting. There's both of you did not take a lot of put on who this is. You should have it here. I don't know. To me, back in the last. All right, SDs, how are you getting started here? 4.5 in the spectroscope. What does that mean to us? Oh, SDs. Sorry. Ready when you are, what'd you say?
You have to convert it to, well, first you have to convert it to angstroms.
Okay, so we're going to convert it to angstroms using, like, what's that conversion?
It's times 1,000.
So we take the spectroscope reading, 4.5, we times 1,000, and we end up getting what?
45.
And that's the little A1, right, angstrom. So from there, and we've done this a couple times, and if you don't quite remember the conversion, I can help you out there to see what we can remember. Hannah, do you remember how to go from here? How do you convert it to meters? Okay. Good. There's a lot of little angstroms, 10 to the 10th angstroms, so 10 billion angstroms in 1 meter. So that's going to give us what? Meters, there we go. So that's wavelength, and then we have to get the energy, so that should now be a piece of cake for you guys. Keep rolling. Ryan, where do I go from wavelength? I can't go directly to energy, so how would I go? How would you like to go? Okay, how do I get to frequency? Okay, so C divided by the wavelength, and that gives me frequency. So C is 3.00 times 10 to the 8th, what? Okay, Elizabeth? Sorry, actually, I can fill this part in when you're going to tell me what the wavelength is, okay? I mean the frequency. I'm going to fill this in here. 4.5 times 10 to the negative 7th meters. Parentheses across this whole shebang. And then when you're ready, frequency. It shouldn't be negative fifth. So here's one thing we should all check first. When you have 10 to the 8th and then divided by 10 to the negative 7th, what does that mean to us mathematically? What should we be doing with those exponents? So when you divide exponents, what are you supposed to do? Subtract. So 8 minus a minus 7 should be 15. But so we know it's going to be a high number. It's going to be a positive high number. So reassess how you put those parentheses in, because that's what it. You guys just don't pay attention when you put parentheses in, and you don't pay attention if the answer even makes sense. So somebody help me out here. 14 sounds much better because it's close to our estimate of a 15. So, you know, you're math savvy. So think first and then calculate and then rethink again. So that's going to be 14. And then what units remaining? Say again? Per second. Because meters cancels here and then the per second. So the slash second remains. And that is frequency. Woo! Almost there. CJ, keep going. Okay, which is? And what is H? Good. Joules time seconds, and then we're multiplying that by V, correct? So I'm just going to use the whole number that Elizabeth gave me because it will keep me from having rounding error. So it's per second. I'm just going to divide by seconds. So CJ, what units cancel? seconds, which makes sense because energy should only be in everybody. What unit? Joules. So when we calculate, what do we get, Jacob?
4.42 times.
Negative 19th joules. Okay, sounds good. And since you guys have done this, like 100 times, you start to notice those common units and common, like approximate numbers. A lot of times our wavelengths are sitting around the negative 7th region. A lot of times our frequencies are sitting around the positive 10 to the 14th region. And a lot of times our energy is in the 10 to the negative 19th region. Because a lot of times we're dealing with visible light. Because the spectroscopes, we're looking at something, right? We're looking up at the light and we're seeing visible light. So you're going to see some of these commonalities. Who's seen that pattern? A little bit? Now, you've done a lot of different types of problems, but a lot of the visible light ones will be this pattern. Good. All right, so talk about the next two, and I would like for you to write out the ion charges. Okay, talk to the person next to you on the next two. Write out the ion charges. Iodine. Iodine. All right, Aiden, get me started. Pick your poison. Which one do you want to do?
I don't know how to do this, so.
Okay, I'm gonna get you started. Look at aluminum. Everybody,
Okay.
everybody, if you don't have a periodic table, I can give you the reference table one, but you need to like physically interact with it. Because if you're always gonna get a periodic table like in front of you, let's say I cover that baby up, you're gonna be lost, right? So you need a periodic table. Okay, if you want a reference table one, it's has a big gap in it, but we know that gap is not. All right, I'm gonna leave it there if you want. So point out aluminum. Everybody, what group is it in? Is in group what? 3A. Okay, so if I look at it thinking electron configurations or look at it thinking how do these electrons build, before I got to aluminum, what had I just passed? Electron configuration wise? 3s2, and then I jump over here and I'm at what? 3p1. So if I actually wanted to write the electron configuration, I'm going to cheat and do the shortcut. So who was the last noble gas I passed? Okay, so bracket neon, right, which to me means 1s2, 2s2, 2p6, and then I fill in the gaps forward to go what? 3s2, 3p1. Okay, so who was my valence shell here? What energy level? 3, right? So how many electrons are in that energy level? Just happens to be 3, right? And you can circle them. You can say there's 2 electrons in the s-shaped orbitals, and there's 1 electron in the p-shaped orbitals. So in the valence shell, there are 3 valence electrons. Okay, so first of all, we've identified it via electron configuration, or what's our other cheat sheet for electron or for valence electrons? The what? If I just look at the periodic table, I should be able to find the valence electrons for anything in a nanosecond. Say again? The group number, right? So what group is aluminum in? 3A, therefore it has 3 valence electrons. So group number is valence electron. Group number is valence electron. So I wanted you to see it, but you also can cheat it, right? So if I'm looking at aluminum, I'm not even to 4 valence electrons, right? That's kind of the break point. 4 valence electrons, I'm going to lose or I'm going to gain. So I'm on the 3 side, right? So what's going to happen? It's losing the 3 valence electrons to become a what charge? Losing 3 electrons loud and proud, please. Positive 3 charge. So therefore, aluminum becomes a 3+ charge as it takes away its valence electrons. That's really your whole thought process. I did it really in a long-winded fashion. You can do it a little shorter, okay? Raise your hand if you can help me with calcium. Anushka. Why does it have a 2+ charge? This is assuming it forms an ion, right? So not just doesn't by itself it doesn't have a charge, only when it forms an ion.
Because it's in group 2, so it would lose 2 to get to the 8.
To octet, right?
Octet, yeah.
So aluminum had 3 valence electrons, so it lost 3, so it backed up to its previous octet. Calcium has 2 valence electrons, so it backs up to lose those 2 electrons to achieve octet again. Okay, and then everybody look at iodine. First of all, how many valence electrons does it have? 7, super close to 8, right? So what is it going to do? Gain how many? 1 to form a what charge? -1. So 7 valence electrons, you're going to gain 1 electron and to achieve octet. And as you gain that 1 electron, you form a -1 as its ionic charge. So everybody in group 1, if they form an ion, is going to be what charge? +1 charge. Everybody in group 5, nitrogen's group, -3. It's because they have how many valence electrons? 5, so they're not going to back up 5, they're going to go forward 3. Everybody in oxygen's group is going to form a what charge? -2. Everybody in aluminum's group is going to, or boron's group is going to form a +3. Okay, so you can predict by just nature of memorizing periodic table like that, or thinking about the electron configurations. They're both going to work for you. This one's more intelligent though, okay? All right, so we can keep practicing with that. We're going to talk about periodic trends for just a little bit of time, and then we're going to do some interactives. Yeah?
For, like, how you write it, does it matter if it's plus or minus?
No, for us it does not. Sometimes in college it's like, you go to the plus first, the negative first, but we're good. Okay, this was a quick review from the interactives you guys did Friday with the properties of metals and nonmetals. So you guys have that written out, yes? Let's add just a couple things to that. This was like part 1 of the 4-part activity we did. This should be in your notes someplace because you were supposed to make it colorful and you know, color coded. I don't want to add all of this. Really, I just want to add the highlighted sections I have here because you guys probably wrote down a bunch of the physical properties. Give me a thumbs up if you wrote down metals or conductors. Thumbs up. Electrical and heat, so that's like thermal and electricity. They're malleable. Thumbs up. Ductile. Lustrous. What's luster mean? Shiny, right? Fancy word for shiny. And solid at room temperature. Okay, so those are the metallic properties you probably wrote down. Those are all physical properties. Non-metallic properties are just opposite of metallic properties. Poor conductors of electricity, poor conductors of heat. Thumbs up. If you don't have this, you want to jot this down real fast, okay? Brittle. What does brittle mean? It'll shatter, right? It'll break. So that's something that just is a common term we use sometimes. Non-ductile, which means that you're not going to pull it into a, what's ductile mean? Not going to pull into a wire. Another thing we should definitely know is that most of them are gases at room temperature. There's only a couple that are liquids. Does anybody know a non-metal that is a liquid at room temperature? Bromine, right. It's bromine too. It's bromine diatomic gas, but it can be a liquid at room temperature. What's the only liquid? Oh, dang it. Mercury is the only liquid metal. There's another one that will melt in your hand. It's not room temperature, but melts in your hand. Gallium. It's pretty cool. Okay, so those are your properties, like the physical properties. The only other thing I want you to denote are the 2 highlighted regions here. And these are technically chemical properties because it's referencing like how chemically reactive they are, meaning how are they going to exchange electrons. So if you have really the ability to lose valence electrons, that means you're very reactive. Okay, and if you're able to gain or share electrons, it means you're reactive. So what we should be able to do is say, well, who's more reactive than the other? Because you have a range of reactivity. So we've actually already talked about this. Who remembers which number of valence electrons are the most reactive of them all? 7 and 1. So if you have 7 valence electrons, meaning you're the halogens, your group 7A, you are super reactive because you are ready to fight somebody for that one extra electron that you need to become the octet and become perfect in all ways. And then who over here is the most reactive? So valence electron 1, which is group 1A, which are the who? Alkali metals. So 1 valence electron, the alkali metals are the most reactive because you're ready to throw your extra electron at anybody who will take it, which means you're very, very reactive. And the reactivity kind of gets smaller as you go towards 4. Thumbs up when you're done here. You just added this a little bit to the table you wrote down, or the Venn diagram you did on Friday. All right, I have to skip a couple of slides, so don't feel like I'm skipping material. It's just stuff we've already talked about, we're going to talk about later. So we know this. Do we know this? Groups. So everybody in group 1, they all have the same ending to their electron configuration, so they all end at what? Number S1, right? Which means they all have the same number of valence electrons. That's how we can say group number means valence electron number. That also means they all have the same characteristics, just the same properties. Okay? So groups have similar properties because their reactivity is very similar due to that number of valence electrons it has. So either know it or write it down, but I'm going to move past this in a second. Okay? So properties are the same because the same. Don't just say electron configurations, but because the same what? Number of valence electrons. Okay? So that's why the periodic table is arranged the way it is, because it gives us an indication of some similarities in groups and in periods. Specifically in groups, though. It's usually a test question people miss. So I was just hanging out here for a second. Okay, so this is stuff you guys already talked about. We know these 4 properties. Hold up your 2 L's. All right, show me the wave. Show me the way. I see some people doing it wrong. Okay, so I got most, okay, so this group 2 is doing great. Okay, so right hand represents what? Radius, and we turn the radius this way, okay? So the atomic radius trend, AR, atomic radius trends this way, and then the rest is the other way. So you have a little picture of your table. Okay, what are the rest? Ionization energy, and, okay, so what you should think about, and some people were trying to tell me, you can put your fingers down, you're good. What some people were trying to tell me last week were the diagonal trends, because there are diagonal trends. I think Kendall's group was like, it's diagonal up and to the right. I was like, what does that mean in terms of groups and periods? So the highest of all the electronegativity, ionization energy, and electron affinity is where on the periodic table? Say again? Top right, because it's increasing up and increasing to the right. So the greatest IE, EA, and EN are up to the right. So like fluorine's area, okay? And then who's the biggest on the periodic table? Who's the largest atomic radius? The farthest to the left and down, so that's the bottom left. So who is that? Francium. So the atomic radius, is largest as you go down and to the left. So there are diagonal trends, but I wanted you to know the very, very much directional periods and groups first. All right, so we've kind of memorized the trend. We know where the largest things are, where the smallest things are, where the most highest ionization energy, and so forth. But now we need to know why. It's like, why do these trends exist? So, because you have to be able to explain them. So there are 2 factors that are the big factors that control why these trends exist. And these are those 2, the last one. Write this down, and then we're going to explain this in depth. Since you took some good notes on your activity on Friday, I would just add this there. Because you already wrote down the trend, you drew your picture. I would just add this there. Let's scroll back down in a second. Let's start back up here top together. All right, so the factors that you would mention if I said what two factors cause the trends, the 4 trends we've been speaking of, the two, like, just simple and short factors are effective nuclear charge and electron shielding. But what is effective nuclear charge? It actually kind of sounds like what it means. The nucleus is charged, right? Nuclear charge. How effective is it at attracting electrons? Because what do positives and negatives supposedly do? Attract, right? So if you have a nucleus that's got 1 proton in it, right? So draw yourself a little hydrogen nucleus. Okay, there's the nucleus, got 1 proton in it, and you have 1 energy level, n equals 1, and in that energy level you've got 1 electron. How is that electron pretty close to the nucleus? Yeah, it's on the first energy level, but there's only 1 proton. Okay, so we've got that in mind. Let's do potassium. Okay, so this is hydrogen. How many protons does potassium have? Look at the periodic table. 19. I am not drawing 19 pluses. We're just going to do 19 protons like that. And draw yourself a little draw yourself a little nucleus right there. And how many energy levels are around potassium? Think about what period it's in. Which one? 4, right? So I'm going to draw this kind of small. 1, 2, 3, 4. All right, so 1, you can definitely tell who is the bigger atom. Simply, just based on rings. Potassium is definitely the bigger atom. Not really, I mean, not only because of the rings, but because it's got more electrons, and so there would have to be 19 electrons in here. I'm not drawing 19. Okay, so what we're looking at right here is yeah, there's 19 protons, but really what's definitely making this bigger, or this atom have a larger atomic radius, is because there's a lot more energy levels, which gives it more distance of electrons out here to the nucleus. So you can really easily tell based on drawing pictures who's larger. But if I'm looking at like ionization energy, which definition of ionization energy was in your reading guide 6? Can you look at that for me? Okay, so the amount of energy required to steal away the most loosely bound electrons. Well, in general, who are the most loosely bound electrons? The inner ones or the outer ones? Outer ones, okay? Because the inner ones are like right next to mama nucleus. They are stuck like glue. They are very well attracted. But you're in the valence shell, you've got you're super far away from the nucleus. You're not very well attracted. So if we're looking at that, so ionization energy, we see this electron that you want to take away, and then you see this electron you want to take away. Who seemingly, based on the distance from the nucleus, do you think is easier to swipe away? Why potassium? It's further away from the nucleus. Okay, so what we're looking at is not only distance from the nucleus, but what's in between this electron and its nucleus? 3 energy levels, right? So those energy levels are shielding, right? So this is electron shielding, aka the shielding effect. Okay, the protons charge, those 19 positive charges, are being shielded from the electron by all of these inner energy levels, these inside energy levels. But look at this proton. Is there any shielding between the proton and the electron here? No, there's no other energy levels blocking it. So this one has a really strong attraction. So it's going to have a high ionization. It's just going to require a lot of energy to swipe that electron away because it's super, super attracted to its nucleus. Whereas this one, what would you consider the ionization energy to be? Higher or lower than this one's? Lower ionization energy, simply because you've got 19 protons that want to attract the electron, but they're stuck in the way. So it just can't effectively attract it very well. So this one has a lower amount of attraction, meaning it's not going to hold it as tightly, so it's not going to take you very much energy to swipe that electron away. So I combined kind of 2 of these reasonings, but I want to give you an example first. Let's do another example though, okay? Let's draw lithium versus fluorine. Lithium versus fluorine, just with these really generic pictures. How many protons in lithium? 3. How many energy levels in lithium? It's in the second period. That means it's the second row. You should be drawing these with me. The pictures help a lot, okay, with some of your more theoretical understanding. All right, fluorine, how many protons? 9 protons. And how many energy levels in fluorine? How many? I hear more people saying 2. Because how many, so in in fluorine, you go 1s2, 2s2, 2p5. So you're still in the second energy level. So there's only 2 rings around fluorine as well. All right, so I kind of draw them the same size just for now because I want you to think about what's happening. So we got 2 energy levels and 2 energy levels, but we've got 3 proteins and a huge number of 9 protons. Right? Did I say proteins? I meant protons. Sorry. All right, so who's going to be stronger at attracting its second energy level? 3 or 9? Who's got more positive charge? Fluorine. Okay. So in lithium, you've got 1 valence electron, and in fluorine, you've got 7 valence electrons. So I'm just going to draw these like this. We do not draw orbital diagrams like this, right? This is 7th grade, but this helps us see the images a little bit better. All right, so I think I put 7 there. All right, so basically what you're looking at is 3 protons versus 9 protons. 9 protons have have 6 more protons that are pulling on the electrons through attraction for positive and negative attraction. So the 9 protons actually have a higher ZEF, which that is what we abbreviated this as. Okay, so effective nuclear charge is talking about the number of protons. If you have more protons, you have a stronger pull on your energy level. So 9 protons pulls on its outer shell really, 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 really well. What do you think that's going to do to this energy level as it pulls it in? It's going to do what? You can see it, right? 9 protons are pulling in its outer energy level very, very, very well. So this is going to shrink in size. In lithium, it's not doing a whole lot. It's 3 protons are pulling a little bit, but it's not, 3 protons got nothing on 9 protons. So this ZEF, or nuclear effective charge, is smaller. The nucleus is not effective. This nucleus is not effective. This nucleus is effective at pulling in its shell. So this one's going to be smaller, right? It's shrinking, it's smaller. And this one's going to remain kind of large. And this is why we do atomic radius this way, because where's lithium relatively across on a period? On the left or the right? Where's lithium, on the left or the right? Left, right? So it's going to be big according to our arrow scheme. And then fluorine's on the top right, so it's going to be over here in the corner of your hand, which is this the smaller side or is this the bigger side of atomic radius? Smaller, which is the effective nuclear charge is making this atom smaller, which is now following our trend. Let me explain that, just the ZEF one more time. What is the Z number? We talked about day 1 of this unit. Z number. Like A to Z notation, it's the atomic number, which is also known as the number of protons, right? So the reason we're calling this ZEF, Z-E-F-F, because it's talking about how the number of protons, Z, is effective. That's why we call it ZEF. So if you ever heard him say ZEF, it's just an abbreviation for effective nuclear charge. All right, I'm going to pause here for a moment. I'm going to let you investigate some more, and then we'll come back to this, okay? Go to the homework part of the website. Because you have the terminology, you just need it needs to sink in before we actually explain some more of it. And it says classwork, periodic PTLE trends, web quest. The new weird PDF viewer on Google is Cami, C-A-M-I. So you just have to log in with your Google account to view it, or log in somehow. So it should be under today's paper. So you're actually going to be looking at the same link that we looked at on Friday, which is the ptable.com. It's very similar anyway. And when it says to look at properties, you see properties, the properties tab. So make sure you're clicking there. That properties tab is going to give you options to view, just like you were Friday, atomic radius, ionization energy, electron activity, and so forth. So, as you can see, which make this a little bit bigger for us. As you can see, you're going to define, you guys have your reading guides, that's why I left those with you. Define, identify, and then try to explain. And then you're going to do that for each of the, there's only 3 that we're doing that for. We're not doing for electron activity. Go ahead and work with a partner on that, so you can have one person pull up the PCV and one person pull up the PDF here. But just write this on your own paper, and then we're going to try to knock out those explanations solidly together, okay? If you need to move to a lab station, you may. I'm going to give you guys about 25 minutes, and we'll see where we are, okay? You want to put those on my, just put those up on my desk, okay? So I should probably hear you discussing nuclear effective charge and electron shielding a lot through these couple of explanations. Sorry, I took that down to the bus. You don't have to work with a partner. I just thought we might want to chat. All right, let's talk about those like rationale explanation based ones, because that's going to really help me see that you got what's going on. You know it. All right, so I'm going to draw like a little makeshift periodic table. That looks great. Yep, there we go. So there's my periodic table, and I'm going to just draw my arrow for atomic radius, so we can speak about these two directions and the factors that relate to them first. So we all know atomic radius trends this way, but now we're talking about why. So on question 4, it mentioned using nuclear attraction, electron clouds, and stuff like that to reference why the radius, okay, so the atomic radius, increases or decreases left to right? Decreases left to right. Because, CJ, pick up. Okay, so I'm going to say because an increasing ZEF. Can you tell me what ZEF stands for again? To the, okay, so ZEF or nuclear attraction. All right, so atomic radius decreases to the left, or sorry, from left to right, because an increasing ZEF, or nuclear effective charge. That just means that the electrons are attracted to more protons. Did we mention electron shielding for this one? or energy levels or anything? Yay or nay? No, because all of these in the period are in the same energy level. So if we're not changing energy levels, we're not changing anything about electron shielding. So in question 7, what'd you guys say, Bailey?
I said, as you move down the group, the medium attraction to electron clouds increases because the radius is
Okay, so the radius is getting bigger because of something else, though. So say that louder and probably one more time.
I said, as you move down the group, the medium attraction to electron clouds decreases because the radius gets bigger and the force increases.
Okay, so I'm gonna have somebody kind of add to that. A new scopes group, or no? Let's go. Yes, you guys.
You said that, like, as the period number increases, as you get everything rectangle, like, there are more energy levels, so it's like spread further out, which increases the.
Right. So we're not saying the radius makes the radius bigger, right? Something else causes the radius to get bigger. So I want to add in one more term. So let me start with what you guys have said so far. Atomic radius increases down a group because there are more energy levels. If I put EL, do you know that means energy levels? Okay. And one more factor. One of the factors I mentioned. Come in. So tell me more. I want you to use the shielding effect here. So increase energy levels, and there is. So we're going down a group, right? So here to here to here to here. Which has more shielding effect? The small one, like the single energy level, or the 4 energy levels? The bigger one, the 4 energy levels, right? Okay, so atomic radius increases down a group because there are more energy levels and there is more shielding effect. And that causes, which is what you were saying, Bailey, this causes lesser attraction. Between the electron and protons. So I'm trying to incorporate those terms. So if we're talking about a period, what is the only factor we are mentioning across a period? So let's remind ourselves, was 4 or 7 talking about the period? You guys can do this, come on. 4, okay, you've got to respond, okay? So this one is talking about the period from left to right, okay? So the only factor we mentioned there was what? Say again? Zeph, or nuclear attraction. All right, and then in a group trend, like down the group, what is the only factor we're mentioning? Energy level, which is definitely 100% related to the shielding effect. So I like to use them interchangeably, but really they're two separate things, but they relate to each other. So if you're going to mention anything about a group, you're going to mention electron energy levels or shielding, and if you're mentioning anything across a period, you're going to mention Zeph. Okay, that's going to continue here. So for I don't know what numbers they were, but for the ionization energy, just give me a quick definition, Corbin.
The amount of energy required to remove it.
Okay, so to remove an electron, right? So I'm going from like lithium, I remove an electron, and it makes lithium cation, right? So another version of it is the energy used to make a cation. So, do you think electrons that are close to the nucleus or far away from the nucleus are easier to get? Far away from the nucleus, right? So there's no attraction there, or very little attraction. So if we're talking about a period, so here's a little periodic table. How did the ionization energy trend? Increasing left to right or up or right to left? So ionization energy increases from left to right or right to left? Left to right. So that's this way, okay? So the trend was increasing this way. There's a reason why, okay? So i.e. ionization energy increases from, oh sorry, I have to actually write increase. Increases from left to right because, what you got, Chandler? Well, tell me what's happening on a period from left to right. Let's say from like lithium to fluorine again. We went from how many protons for lithium? And then how many for fluorine? 9. So what am I trying to get you to say? Increases what? which we call that a fancy word. Zeph. Okay, so ionization energy increases from left to right because Zeph, which dumb that down for me, means nuclear attraction, okay? Nuclear attraction. All right, so what happens to Zeph as you go from left to right? Everybody should be able to tell me this. It increases. So the energy it takes to rip an electron from your atom is increasing because your nuclear attraction's like, no, don't take me. So the increase in the nuclear attraction is increasing. And I'm just going to add a little bit more to this, which causes a stronger hold to electrons, or on electrons. All right, so then why is the electron affinity, or ionization energy, increasing up a group? All right, so one thing to mention, period, like left to right, what's the only factor we mentioned, Chandler? Say again? The Zeph, right? That's the only factor we're mentioning on period. So what is the only factor we're supposed to mention on group? Shielding. What you got, Corbin? On this group here, going up the group. So ionization energy increases, actually, let's do it this way. I'm going to go down. Decreases down a group because why?
There are more, because like the energy levels are further away from the protons.
So give me the other term we're supposed to kind of use with energy levels. Shielding. So ionization energy decreases down a group because there is less or more. Less or more. Less shielding would mean that I'm really close to the nucleus.
Oh, more.
Right, there's more energy levels in the way. So because there is more electron shielding due to increased number of energy levels. So I kind of like pull those together. Alright, so are you guys getting the point here? If you're mentioning anything across a period, so like sodium versus magnesium, or phosphorus versus chlorine, or lithium versus fluorine, anything across a period, you're only going to explain with what factor? Zeph, or nuclear effective charge. And if you're looking at a comparison down a group, like lithium to cesium or nitrogen to phosphorus, you're looking down a group, what's the only thing you're supposed to be mentioning? Shielding, or looking at how like many energy levels there are there. Now I could do this for the other two, but you're supposed to see the trend here. Okay, so now handwrite everything else so that you could like see and think about how I would expect you to explain something like on a free response part of the test. Okay, do me a favor, pull up PS6. I have it here for us as well. Just figured you might want to see it. Alright, have a periodic table out. I'm going to get you started on this little table. It's about partially halfway down the yes. So you're supposed to get a little bit of PS done so that you can understand a little bit more about what you're talking today. That vocab section up there is not too hard. So that's why I'm starting down here. Alright, so pinpoint on the periodic table. Where's lithium, beryllium, boron, and carbon? Where are they at? They're all in what? Period 2. They're all in the same period, right? So I'm just going to kind of indicate that like this. This is period 2. This is kind of how they're arranged, right? So I know how to do atomic radius, ionization energy, blah blah blah. I'm going to skip the most metallic one for just a hot second, okay? So of these 4, who should have the largest radius? Who? Lithium. So atomic radius, you might even, on your periodic table, draw yourself little arrows. And so why is lithium the biggest? Just tell me one reason. Do not say it's because it's farthest left. I got that. I want to know the background, the reason. Lowest Zeph, that's it. Don't have a lot of protons, that fake is large because it can't attract its electron cloud. So lithium is the largest atomic radius, okay? Who's going to have the highest ionization energy? Carbon, because I know you're going to say because it's farthest to the farthest to the right in our little trick, hand trick thing. But why? Say again. Highest Zeph. If you have most electrons, you're not taking my electrons from me. Or highest proton, you're not taking my electrons. It's got the highest energy, ionization energy. So this is the highest ionization energy. Lithium was the largest radius. Okay. Lowest electronegativity. Why lithium? Why is lithium the lowest electronegativity? Lowest Zeph. It's like, nah, I don't really care to share electrons or want electrons, you can have them. So it doesn't have a high want for electrons. And then highest electron affinity. Who is it? Carbon. Because highest Zeph. Electron affinity means that you want electrons, you desire them, you're willing to steal them. So carbon would prefer to steal electrons. It had to take 4, but it's more willing to take electrons than lithium. Lithium doesn't want electrons at all. What does it want to do? Remove one, right? Give them away. All right, so that's what you're doing across the period. Look at the second one. Beryllium, yes. I'm going to go right back to that in a second, okay? Beryllium, magnesium, calcium, and strontium. Go ahead and classify that one. Beryllium, magnesium, calcium, and strontium. Try to answer those last 4. All right, who's got the largest atomic radius? Who? Strontium it is, right? So we're looking down a group. Why does this one have the largest radius? What factor? Shielding or energy levels, right? It's got like 5 energy levels, so it's got a lot of shielding, so it remains large. Who has the highest ionization energy? Beryllium, because it's teeny tiny. You're not taking my electrons. I'm super attracted to my protons. Okay, who's got the lowest electronegativity? Strontium. It's so far away. Low. Its valence shell is so far away from its nucleus, it does not really have any pull for any more electrons, which just because it's so far removed. And then highest EA. Who? Beryllium is right. It's going up. EA is trending up, and it's got to be because it has least energy levels, right? Okay, so least shielding. All right, so that's going to be easy to do if you know your hand trick and you can kind of rationalize some of that. So I'll tell you for most metallic. I'll come right back to this. I had a nice periodic table, but I'm going to let you read that first, and I'm going to draw my periodic table. So the characteristic of metallicity, or to mean it's acting or behaving as a metal, just means that it loses electrons. And that's the very first thing we talked about today. Metals lose electrons. So who's going to lose electrons? The things on the left side of the periodic table. So metallic characteristic is increasing down and to the right. Who does that follow? Atomic radius, right? So that's why it's just generally the same in that same direction as atomic radius. So if you're non-metallic, that means that you like to not lose electrons, gain electrons, right? All those non-metals we mentioned, those were all 5, 6, and 7 valence electrons, so they wanted to gain. And then that's going to follow the same trend as everything else, up and to the right. So from the most metallic in this number 1, who should be most metallic? Lithium, right? It's the farthest to the left and down, which in this case farthest to the left. And who should be most metallic in number 2? Strontium, which lithium's like, heck yeah, let me lose 1 electron. Beryllium and carbon, they don't care. And then strontium's going to lose electrons because it's so big, its valence electrons are so far away from its nucleus, it doesn't even know it has a nucleus, it's going to just fall off. which means that they're gonna be likely to lose electrons. All right, do you guys doing your problem set? Yeah, okay. Keep working for a minute. I'll get announcements up here. You can see homework is just finished. PS